Okay, so how is everyone today? Good? All right. So today's, wow, September's gone, isn't it? So today's the 1st. All right. So last time we ended with singing the quadratic formula. So that's something that you're expected to know. And just to remind you of that, we could say something like this. Let ax squared plus bx plus c equals 0. Consider that equation with a non-zero a. So it's okay, it's permitted that b could be 0 and c could be 0, but a has to be non-zero, because if a were 0, then we wouldn't have a squared term, and so it wouldn't be a quadratic. The solution is given by this formula. X is negative b plus or minus the square root of b squared minus 4ac over 2a. So this formula is called the quadratic formula. So let's use it real quick. So please solve. X squared minus 16x minus 80 is equal to 0. And in fact, I'm going to do it in two different ways. So I want to do it by factoring one way. And then in the right column, I'm going to use the quadratic formula. So it's particularly easy to do it by factoring. So how does that factor? So we know that that quadratic's got to factor somehow, so that the result will look like this. So x something, x other something. So what goes where? Yeah, so minus 20 and plus 4. All right. So because we're able to factor it like that, that means that we have the product of two things is equal to 0. So at least one of them is 0. So this equation splits into two possibilities, and we get two solutions. X is negative 4, or x is 20. So pretty straightforward. But now we're going to do it with the quadratic formula. And if the quadratic formula is correct, then, well, we should get those answers, right? So in order to use the quadratic formula, we need to identify the values of a, b, and c. So for this particular example, what's a? 1, and b? Negative 16, and c? Negative 80. So it's just a matter of using the formula then. So it would be negative 16 plus or minus the square root of negative 16 squared minus 4 times 1 times negative 80. All over 2 times 1. All right. Then that thing in the radical, I'll use my calculator to evaluate that. So negative 16 squared minus 4 times 1 times negative 80. That's 576. So that'd be 16 plus or minus the square root of 576 over 2. And now, Does 576 have a square root that you know? Or can you type it into your calculator? Okay, so then what is the square root of 576? 24. So it would be a good idea for you to memorize the squares of all the integers up to maybe 25. So like 576 is a number that you should know. Ah, that's 24 squared. All right. So 16 plus or minus 24 over 2. Now, understand the meaning of that. That means that there's, in fact, two possibilities. So now I'm going to split them into the two possibilities. One possibility is when you take subtraction. So then it would be 16 minus 24 divided by 2. The other possibility is when you take addition. So x is 16 plus 24 divided by 2. Okay, and then we want to simplify these. I'll do the one on the right first since it's a little easier. 16 plus 24 is?
40.
40 divided by 2 is? 20. And then 16 minus 24 is?
-8.
And then divided by 2 is? -4. Okay, so do you see? Yeah, we got same answers. All right. Now, looking at this example, you might say, you might say like, wow, I don't see any reason to ever use the quadratic formula, right? Because evidently I was able to do this here, okay, and I got to the answer, and it was, I think, clearly less work than this. All right, but the only reason why that happened is because when I was writing this down, I made a conscious choice that made it easy to do it this way. Okay, so now I'm going to not do that and give you this example. So, for example, so I could say, consider the following. Consider 3w squared minus, I don't know, 5w, and then minus 17 equals 0. So 2 requests. First request is to factor just this part. And then second request is to solve the equation. All right. So if you look at what we did on the previous page, that's essentially what we did. Is we said, okay, here's this quadratic equation. If I can factor that, and we were able to, then that makes it quite easy to solve the equation. So if you can factor, you can solve. Now, off the top of your head, can you see how this is going to factor? Probably not, unless you're quite good. So in the first place, this example is not monic, meaning the leading coefficient is not 1. So it's slightly more complicated than usual. Further, and because of that, we would be looking for two numbers whose product is 3 times -17, and whose sum is 5, -5. Now there aren't any integers that do that. There are some numbers, but there aren't any integers. Okay, so here's what I want you to observe, is that usually we do 1, which is to say we factor in order to answer 2. Okay, that's what we've done until now. So now we're going to do 2 with the quadratic formula in order to answer 1. All right. So that means that we're going to have to answer part 2 first. So using the quadratic formula, we need to identify the coefficients a, b, and c. So what's a? 3, and b, -5, and c, -17. And then now, the quadratic formula is stated when the variable is x, but in this exercise the variable is w. Does that make any difference? It doesn't make any difference. Except you've got to write w equals instead of x equals. So that would be -5 plus or minus the square root of -5 squared minus 4 times 3 times -17 over 2 times 3. So again, that's just arithmetic. So my calculator is saying 229. So W is 5 plus or minus the square root of 229 over 6. So now, does 229 have a integer square root? It doesn't. But when you've memorized the squares of the first few integers, you should be able to tell what numbers this is going to be between. So what's the square of 15? 225, right? And what's the square of 16? 256, right? So whatever this number is, it's got to be between be between 15 and 16, right? Because 15 squared is less than 229, and 16 squared is more than 229. So just to make sure that we have the right idea, if I type that, when I press enter, I should get some number that's between 15 and 16. Okay, good. So now I want to write down the two separate solutions. One of them is 5 minus the square root of 229 over 6. And the other is 5 plus the square root of 229 over 6. All right. Any question about finding the solutions? Now, to answer part 2, or I mean part 1, because we answered part 2 first, what we're saying is that 3w squared minus 5w minus 17 should factor, just like all the other times that we factored something. And it's going to factor in this way. It's going to be w minus something goes in that slot multiplied by w minus something goes in that slot. So what goes in those two slots? What do you think? Well, we've got two solutions, right? We've got two slots. That's where they go. So I'll put this one right there. That one right there. So 5 minus square root 229 over 6. 5 plus square root 229 over 6. And now this is almost correct, but it's not correct yet. So now the fact that these solutions don't end up being something nice like like 8 and 7 or what have you, that's why if you were to try and factor this in the old way, the way that you already knew how, it wouldn't really work out unless you were unless you could just were so good that you could just see these numbers, which is why the quadratic formula is useful. But so just cover those up for a moment because they're sort of distracting to look at. And imagine we've got this binomial multiplied by that binomial. So you could, in principle, use FOIL to multiply out and collect like terms right now. And if you were to do that, what would the coefficient on the squared term be, as it's currently written? Right, because you get w times w, that'd be a w squared, and then w times that number, that'd be something, and then w times that number, that'd be something, and then these two numbers multiplied together. What would be the coefficient of the squared term? It'd be 1. But we don't want it to be 1. What do we need it to be? We need it to be 3. Why do we need it to be 3? Because that's what it says, right? So, to make this right, you have to put the 3 there. Okay. So the point of this exercise, especially doing this exercise, this very easy one, and then comparing it to this one, is that I want you to see something. Is that to start out with something, the way this is taught, to start out with something that's not too hard, you learn how to do this. You learn how to factor these, but that factorization only works when the quadratic is sort of very nice. Okay, when it's sort of made to work. And then if you can factor, then you can solve. But generally, the process works exactly in the opposite order. And that is that usually it's not easy to factor these things. It's not easy to do that. So what you actually end up doing is you use the quadratic formula to solve it. And then once you have solved it with the quadratic formula, that tells you how to factor it. It's actually exactly the opposite of what you might suspect. Any questions about this? Yes?
On the test, is that going to be specified?
What?
Like, is it going to say factor and solve as the question, or is it just going to be that giving you and you have to guess?
Well, I mean, it could be the instructions could be either one or both.
Will
It could
tell
be.
you which one?
Yes, it'll say it'll be clear about which one is requested. So you can factor a quadratic. That's the kind of thing that you can factor, and you can solve an equation. But it doesn't make any sense to factor an equation. That's not a. That doesn't make any sense. Okay, good. All right. So now, concerning that formula, negative b plus or minus the square root of b squared minus 4ac, all divided by 2a. This expression that is under the radical is important enough to have a name. And now we're going to talk about it a little bit. So the expression in the radical is called the discriminant. And it's denoted with a d, so d is b squared minus 4ac. All right. So now, as an aside, we haven't talked about it a lot yet, but we eventually will. When we get into plotting things a lot, y is ax squared plus bx plus c. When you plot this, so it plots as a characteristic shape. So I'm going to give a few examples here. So the simplest one of these is when you take the monic case, which is to say that A is 1, and then set B and C to be 0. So that's the case of y is equal to x squared. So it looks like, so that's the equation. So what if we plug in x is 0, then what's y? 0, right? And what if we plug in x is 1, then what's y? Just 1, right? And what if we plug in x is 2, then y is 4? What if we plug in x is negative 1? Then y is 1 again, right? Because squaring negative 1 gives you 1. And squaring negative 2 gives you 4. So if you were to plot lots and lots of points, it would look like that. And what's the name? This shape is so important it has a name? Parabola. And when we start plotting a bunch of stuff, we'll see how you can take a shape and, you can take a shape and you can sort of move it around on the axis so that you can move it up and down, left and right, and you can stretch it out and do various things. So there's a parabola that would, look like this. So we sort of moved it down and to the right and then stretched it out a little bit. And you can, besides moving it around and stretching it out, you can also turn them all the way upside down. And it's these two kinds of possibilities that I want to draw your attention to. Specifically that this kind of plot, this parabola, is a parabola that, if you can imagine it, would hold water, right? Whereas the other kind would not hold water. Water would shed off of it. And so these two different kinds, the kinds that would hold water and the kinds that wouldn't, that is entirely determined by A. So specifically, ones that are like that, it must be the case that A is positive, and ones that are like this, A is negative. The leading coefficient. And the way that I remember that anyway, it's that instead of writing the A less than 0 down there, I write it up here. And then I note, doesn't that look like a frowny face? Mm-hmm. And negative people are frowning. Yeah. And then this one right here. Look at that. Look at that smile. See that? Positive people are smiling. So another way to say this is that this parabola opens down like a frown, and this one opens up like a cup. So that's how they look. That being said, y'all talked about with the substitute instructor about complex numbers. So in particular, the square root of a negative number when complex numbers are permitted, that gives you an imaginary result, right? Like the square root of negative 16 is 4i or negative 4i. But at any rate, the square root of a negative number has no real answer, right? So now I'm going to make a table down here, and it's going to have 2 rows and 6 columns. 2 rows and 3 columns for a total of 6 items. So now, concerning A, because we want this to be a quadratic, A can't be 0. So I'm going to say that the two possibilities are A is negative and A is positive. So those are the two possibilities. And then concerning sign, the discriminant can be negative 0 or positive. So D could be negative, D could be 0, D could be positive. So 6 possibilities. Now in each table location, I'm going to draw a horizontal line. And this is going to be the horizontal axis. All right. So now, in these pictures up here, these example pictures, you can see that, for example, this parabola hits the horizontal axis twice. It's the horizontal axis twice. So this red is the plot of some y is ax squared plus bx plus c. This horizontal axis, it has an equation also. What's the equation for the horizontal axis? Y equals what? Y equals 0. So if you want to know the places where y is 0 and y is ax squared plus bx plus c, visually what you're asking is where is the red parabola and the graphite horizontal axis, where do they touch? Well, they touch in 2 places, right? Here and here. Now these locations where those 2 touch, those are important enough to have even another name called x-intercepts, right? And here's the deal, is that solutions to an equation, to a quadratic equation, are in correspondence to factors of the quadratic, and also are in correspondence to the x-intercepts in this plot. So, if the discriminant is negative, the thing that's in the radical is negative, then how many real solutions can there be if the discriminant is negative? None, right? There cannot be any. So now, in this row, this is the row where all the parabolas open down, right? And this row is the row where all the parabolas open up. So in this picture right here, can you draw a parabola that opens down And also, because the discriminant is negative, never touches the horizontal axis. So it opens down and doesn't touch the axis. How about this kind? So it never touches. All right. Interesting. Now, for this position, we want to consider the discriminant being 0. So in this formula, if the discriminant is 0, well, what's the square root of 0? 0. So the formula would be negative b plus or minus 0. So it is as if that part is not there. So there'd just be one solution, right? And the solution would be negative b over 2a, because the discriminant is 0. Now what I want you to imagine is take this parabola, and if you just wiggle it up and down just a little bit, it still has no intercepts. But if you grab it and just pull it up just very slowly, then it'll come to rest to where it's touching the axis at exactly one point. So can you see that if you move the red up, it'll touch the axis at exactly one point? It will look like this. All right. Now, this red parabola, for example, if the discriminant was 49, then what's the square root of 49? 7, right? So that the solution would read negative b plus or minus 7 over 2, and then all over 2a. So there'd be two possibilities, the one where you say subtract 7, and the one where you say add 7. So if you take this parabola in the middle and you move it up, then how many intersections will there be? There'll be 2. All right. And so now this row is just the same, except all the parabolas need to do what? They need to open up. Okay, so I'll just do that very quickly. So what I want you to see from this is that if the leading coefficient is negative, that means that if you were to plot it, the parabola would open down like a frown. And if the leading coefficient is positive, the parabola would open up like a cup. And if the discriminant is negative, how many real solutions are there? None. What if the discriminant is 0? It would be exactly 1. And if the discriminant is positive, how many? 2. Okay. So the discriminant is telling you a great deal about how the parabola will behave. Any question about these things? All right. So now we're going to solve some equations that aren't quadratic. Okay. So this is section 2.6, I think. So other types of equations. So it's called other types of equations, mainly, I suppose, because we were just talking about specifically quadratic equations. So I want to make some brief comments about just equations generally. So if we say let a equal to b, let a and b be real numbers. And also let C be a real number. So we could consider this equation, A equal B. Now notably, remember that that writing an equation down doesn't mean anything about false or true, because the equation could be false, it could be true. So an example of a false equation would be something like 3 equal 8. An example of a true equation would be something like 8 equal 8. Okay, now, if we take these equations and we add C to both sides, and to give a concrete example, how about 4? So we'll add 4 to both sides. So this equation, 3 equal 8, what's its value? False or true? False. And then now I'm going to add 4 to both sides, and I get 7 equal 12. All right, and how about this one? Still false, right? So what I want you to observe is that this equation started as false, and then we did something. We added 4 to both sides. The result in the end was false. Okay, similarly, 8 equal 8, that's true. Add 4 to both sides. Now the equation reads 12 equal 12. So we began with true, and we ended with true. So what I want you to take away from this is that it's always permitted to add a number to both sides of an equation, because, in the end, if it was false to begin with, it will be false in the end. And if it was true to begin with, it will be true in the end. So you don't have any kind of worry that you might modify the truth or falseness of the equation when you add the same number to both sides. Let's see, what about A equal to B, and we're going to consider multiplying both sides by C. So that, we'd have AC equal BC. All right, so again, 3 equal 8, 8 equal 8. Instead of add 4, we'll multiply by 4. So this will read, 12 equal 32. So we started with false, multiplied both sides by 4, we ended with false. So that's good. Multiplying by 4 didn't modify the truth value. 8 equal 8, that's true. Multiply both sides by 4, we get 32 equal 32. That's still true, that's good. But there's something that's the complete story has not been told, actually. Because there is in fact some number that it's not permitted that you should multiply both sides by this number. What won't be permitted? 0, right? Let's consider. How about we take this equation? So that's an equation. What's its value? False. Suppose we multiply both sides by 0. What's the new left-hand side? 0. What's the new right-hand side? 0. What was the value of the equation we started with? And the value of the equation that we ended with? True. That's a big problem. So now, concerning these little pairs, right? Going this way is adding 4. Going that way is subtracting 4. So adding 4 and subtracting 4, those are fine. Here, going this way is multiplying by 4. Going that way is dividing by 4. Multiplying or dividing by 4 is fine. This is multiplying both sides by 0. That's dividing both sides by 0. Neither one of those is okay, because observe that you can modify the truth value. Okay? So in fact, the rule is that you can multiply or divide by any number that you like, so long as that number is not 0. Okay? Finally, the last thing that we're going to want to do is we're going to want to take an equation and then square both sides. Or just generally raise both sides to some exponent, but squaring is good enough, is important enough that I'll single it out. And then the question sort of is this okay? Can we do this? Well, let's consider. How about 3 equal 8 and 8 equal 8? So what do we get if we square both sides? For this one, what's the new left-hand side? 9, right? And the new right-hand side? 64. So it started false and ended false. That's good. And then for this one, if we square the left-hand side, we get 64. If we square the right-hand side, we get 64. So it started true and ended true. That's good. But I claim actually that there's a way that we can break it. There's a way we can break it. How can we break it? Let's think here. It has to do with, for example, here's an example of the area that gets messed up. So what's the square root of 16? 4. So in particular, 4 is the only answer when the question is, what's the square root of 16? But now there's something else that squares to become 16. What? Negative 4, right? But when you say, what's the square root of 16, the answer is not plus or minus 4. The answer is 4. Yet, both of those square to become 16. So how about this equation? Negative 4 equal 4. Is that false or true? It's false, right? It's false. But if we square both sides, what's the new left-hand side? 16. And what's the new right-hand side? 16. So what I'm showing you is that you could have an equation that's false, square both sides, and then the result is true. Very interesting. So concerning these things, what I want you to take away from this page is that it's always going to be fine to add the same number to both sides or subtract. It's always going to be fine to multiply or divide both sides of an equation by a non-zero number. And then squaring both sides, that's something that we're just going to have to note every time that we do it. And we're going to need to check carefully whether or not that broke something. Okay? But what I want you to see is that it's possible to turn a false equation into a true one if you're not careful. All right, so let's have an example of solving an equation. All right. So the example is solve the square root of 15 minus 2x equal to x. All right, interesting. So now, here comes a step that we've never done until now, because it's in a sense never been necessary until now. So note, for example, could 10 be a solution to this equation? No, it couldn't be. Why could 10 not be a solution? Why? Right, because this equation isn't even defined at 10. Okay, because you know, the rule in the class is that all problems, all exercises occur in the real numbers unless we explicitly say that we're working in the complex numbers, which means that it's not permitted that we should have a negative input to the radical. So 10 could not be a solution. 0 could be, in principle, it could be. If you were to evaluate this equation at 0, we'd have square root of 15 equals 0. So that's defined, but it's not true, right? So that means that 0 is not a solution. So the first thing, the first order of business, is to find the natural domain of the equation. So we'll do it by each side. So what's the natural domain of the left-hand side? What must be true in order for the left-hand side to be defined? Well, whatever is in the radical, that has to be greater than or equal to 0, right? So that's what we need to write down. 15 minus 2x greater than or equal to 0. And so now we need to solve that. So that'd be 15 greater than or equal to 2x. And then divide by 2. So that'd be 7.5 greater than or equal to x. Okay, and then you could write that in interval notation as what? Oops. So you could flip it around and write it like this. So that'd be negative infinity to 7.5 like that. What about the right-hand side? So ignoring the left-hand side and just looking at the right-hand side, what's its natural domain? All reals, right? So we need both of those to be true. The left-hand side has to be able to be evaluated, and also the right-hand side. So we can compute the intersection there. So what's the intersection of those two? Just that one, right? So it's for that reason that 10 is not even among the choices. Okay, the biggest possible x is 7.5. It doesn't even make sense to consider a number bigger than 7.5. Okay, notably, we haven't actually started to solve anything yet, right? Okay, so now we're going to do some algebraic steps, and we're not going to finish it. We're just going to get started. But I want you to see. I want you to see what happens. So here we have this this equation. I'm just copying it down. And more or less, the thing that we need to overcome is the fact that there's a radical, and in particular, we have variables in the radical and also out of the radical. So we need them to all either be in the radical or they all need to be not in radicals. So how can we deal with it? Yeah, we could square both sides, right? We could do that. But what I want you to sense and to note is that doing this, squaring both sides, is a little bit fraught with problems, because, well, when you simplify the left-hand side, it becomes this, 15 minus 2x, and then the right-hand side is x squared, and if we move all the terms to the right-hand side, then it looks like this. And everything looks good because now we've got a quadratic equation, and after all, didn't we talk about solving quadratic equations? But the problem is, and I want you to think about why this is a problem, is that moving from here to here, what did we do? We squared both sides. And on the previous page, we established that if you square both sides, you could have started from an equation that was false and turned it into an equation which was true. and that's going to mess stuff up, and we're going to have to figure out how to fix it at the end. So we'll have to see what that means next time. Have a nice Monday.